Good afternoon. Okay, I'll be doing, like I said on Wednesday, I'll be doing Dr. Hafka's lecture today. He'll be back on Monday. So I also I received some of your mails on the topology lecture, and I'll give them to Dr. Haftka as soon as he gets back. So he'll probably clarify some things, and I think he'll probably give you an extension on the deadline for the bonus problems on the topology. So one other thing, somebody in class suggested that I reorganize the way the bonus problems were posted. So from now on, we'll just do it in this way. So if you look at the discussion thread for the bonus problems, you can sort it by date, so that the last few threads show up first. And you'll see that for each bonus assignment, there'll be a lecture number, and if you look at it threaded,
what is threaded and unthreaded?
Threaded just shows it as a tree. Okay. So where do you set where it shows more per page? Settings? Edit paging, okay. Okay, so if you look at from Wednesday's lecture, the posting will be as follows. You'll see there's a bonus assignment of a lecture date, and then if you expand that, the question 1, question 2, question 3 will be sub-threads to that. So if you want to post an answer, you just reply to whichever one you want to answer to, and then if you want to vote for one of those answers, you just reply to that answer. So it'll be like a tree. You just vote accordingly to that. Is that better? Okay. I don't know. I haven't seen a way to move the old postings, so, but in the future, just post in this manner. Okay. Okay, so just go on to the lecture. The lecture today is on a sequential nonlinear approximate optimization, and basically this is just a generalization of the SLP method that I presented in the last lecture, and the approximations that are used are quadratic instead of linear. The same approach is used where you only approximate the expensive functions. So if you have a function like the weight calculation in the beam problem that is cheap, you won't approximate it. You'll just approximate something that takes a lot of computational power. So the formulation is basically the same as well, and the method is also, you start with a trial design x0, and you approximate the expensive functions around that point, and then you optimize from the approximations. So if you look at the formulations, you have objective function, your constraints, and again some move limits. Just to clarify things, the paper I gave you for the reading assignment has a lot of information, and it's a review paper, and what it did is it tried to collect all the methods you can use to solve this SQP problem with. So there's no best way of doing this. If you look at the MATLAB help page, they give a few more references on what you can use to solve it, and they also give their own method, and that's a fairly good way to look up how to do SQP as well. If you want to look into it further, is just to go look at the fmincon help file in MATLAB. So in the review paper, at the start of the paper, they give you a few assumptions that is needed to just to define the type of problems which the algorithm is suited to, and it also gives you the limitations of the algorithm. And some of these assumptions are, well, the most important one is that in the nonlinear programming problem, the functions that you approximate need to be 3 times continuously differentiable. And they also have to be very strong second order sufficient. And this strong second order sufficiency is required for the convergence of the algorithm, the convergence of the quadratic programming problem inside the algorithm. If you don't have this, you'll end up with a lot of local minima that the solution may be converging to. So there's
C cube is third order differentiable.
yes. So if you differentiate a function 3 times, it'll still be continuous.
And then what is strong second order sufficient?
That refers to the Hessian. So you remember the lecture I gave on the Lagrangian, what the sufficiency conditions were? It's also given in that section of the handout that Dr. Haftka gave you. So let's go look it up, and it'll be defined in there. This strong second order sufficiency. So the basic algorithm, there's a close correspondence to Newton's method for unconstrained optimization. The basic steps that are taken in this algorithm mimics Newton's method. So, and that's also one of the bonus questions at the end of the lecture, is you have to go look it up and just compare the two and see where the agreement between them are. So basically, the algorithm starts with a initial point and an approximation of the Lagrangian function at this initial point is made, and this is done by a quasi-Newton method or BFGS updating. BFGS is a fairly popular way of doing this, and that's also the way that Fman-Khan handles it. And then from this approximation, a quadratic programming problem is constructed and optimized. So this is a sub-optimization within the main optimization. I won't go into this sub-optimization. There's a lot of ways of doing that, and they are given in the review paper. And there's also a method discussed in the Fman-Khan help page if you're interested in that. So this optimization, this sub-optimization gives you a search direction. And this search direction depends on where you are, if you're near to constraints, if you are on a constraint. If you're on a constraint, you're going to slide on along the boundary of this constraint. If you're not next to a constraint, you're going to take a sort of a direction that's analog to the steepest descent method. And if you look at the review paper, there's several methods of solving this QP problem. And then from the search direction that you obtain, you perform a line search in the problem space. And this line search is performed using a merit function, which I'll get into later. And the solution of that merit function along that direction is used as your next starting point for the outer optimization. Are there any questions so far? No. So to start off, at the first point, the Lagrangian function is constructed, just the same way you used to, and then the Hessian of the Lagrangian is calculated, and the gradients, sorry, not the gradients, the constraints are incorporated in this, of course, and this forms a QP problem, quadratic programming problem, which is solved and a direction is obtained dk.
The constraints are the subject to part, right?
Yeah.
Why? So you reformulate the constraints in this case?
Yes, you incorporate in Lagrangian.
And in this case, the constraint is formulated to be less than 0, thus the negative sign missing from the
yeah, the quality constraints and the inequality constraints are incorporated in there. So, and during each time step of the outer optimization, K, the Hessian is updated. And this updating is discussed more in detail in the FMINCON help page. It's a lot more clear in there. But basically this is done through a quasi-Newton method or BFGS. And also for the Hessian, you try to maintain a positive definite Hessian, and this is done by manipulating this Q vector. So basically you want to, SQP just, it fits a quadratic polynomial through the data. So if you have a more or less convex Hessian, you can easily fit it, your approximation through it, okay? So if you have something that's not positive definite, like this, you'll end up with some numerical errors when you try to fit your quadratic solution through there.
Could you fit a polynomial through a negative definite surface?
Yeah, but the problem there is if you do that, if it becomes negative, your optimum will jump around. So if you have something where you start off far from the solution and you try to fit it through here, you'll use in one dimensions you use 3 points and you use that to construct a polynomial, and then you obtain a solution somewhere there. So the algorithm will jump to this point and then it'll try to approximate it there too. But if you have a very complex problem space where you have a numerical noise or local optima, so you jump from here to here, you'll end up with a reversal of your polynomial, and you'll probably end up jumping to your move limit because this answer will be better than that or to this side. So you'll end up jumping around with the algorithm. So that's why they try to maintain it as positive definite. So for the solution of the quadratic programming problem, you'll try to minimize this Q vector that was given in the previous slide, and that'll be subject to your constraints. So this A matrix is the combined inequality and equality constraints, and this is also given in the both the reference material and the FMINCON help file. So basically A is updated each iteration, and the solution of this problem will give you a search direction dk, and you're going to search along this direction in the problem space to obtain your next point. So to perform the line search, you use this direction along with a step size alpha, and whatever you multiply this direction with will be your step length. And in FMINCON, the particular merit function that's used in FMINCON is this one, and as you can see, it incorporates your objective function, equality constraints, and whichever the inequality constraints which are violated. So if none of them are violated, you'll simply get a 0. If one or more of them are violated, it will be summed and penalized. So you see there's a penalty as well for both of the inequality and equality constraints, and this penalty in MATLAB is calculated using this function, and this is just one of the Lagrangian parameters. You can look it up. I'm not going to go into detail on that. So just to give an example, this one is also given in the MATLAB documentation. You can see that even for a starting point that is in a infeasible region, it will still be able to find the optimum. And the one thing about the SQP is non-constrained problems will usually take, or will converge a lot quicker than, unconstrained problems will converge a lot slower than constrained problems because of the extra information the gradients, not the gradients, the constraints give the algorithm. And there's also a demonstration of that in MATLAB. So as you can see that it steps out of the infeasible region after a few iterations, and then it starts converging on the solution which lies on the constraint boundary. And this is the Rosenbrock function with a added constraint. So some limitations on the SQP algorithm. It is only suited towards real valued continuous problems, and it's a local optimizer. If you have a global problem and you start it at different points, you'll get different optima depending on where you started, if and what region of the local optima you started at. It doesn't. The SQP algorithm also, it does not cope very well with numerical noise. As you start shrinking down the move limits, you also have the same problem as I discussed in the SLP lecture. The method requires gradients, unlike PSO or GA, which don't. You'll have to have either a function that'll give it the gradients, or you have to use some sort of finite differencing method to obtain the gradients. And this is also coupled with the numerical noise. And it also requires fine-tuning of the maximum step size and the rate that it shrunk at. So for some of the problems that we did, we found that it will not converge unless you play around with the maximum step size in fmin_con. So that's just something to remember if you ever have problems with the algorithm. Okay, the advantages are it's very fast compared to GA or PSO. It's very fast and it's very accurate. You don't have to specify any method like a penalty method where you have to specify the penalty itself and any rate that it's reduced or increased at. This is taken care of internally in the algorithm itself using the equation that I gave you a few slides back. And like the example shows, it does not require a feasible point to converge. And it usually converges faster if you have a lot of constraints. So for the bonus problems, like I said, I'd like you to just see what the similarities between this method and Newton's method is, and just give me a sentence on each and discuss it. A lot of that is also given in the reference material that I posted. And I sort of answered this. Why is it important to keep the Hessian of the Lagrangian function positive? Yeah, you can just look into that too. And then discuss some of the practical methods to improve the reliability and efficiency of SQP. This is basically what you did in some of the homework problems, like you normalized the constraints, you normalized the design variables, you reduced the search space. Dr. Hafka's Quater I don't know what he calls it, where you have the answer, where you basically know where the answer is. So you can use that to give it a starting point, and you know that that starting point will be more or less near the optimum. So it'll help the algorithm converge a lot faster. Those type of considerations, just give me a few and discuss them each.
So, sequential quadratic is a local optimization.
Yes.
So, when you do in a practical situation, you run a PSO or you run a genetic algorithm, you go find a design. A lot of times those don't converge to the exact optimum. Do you then say, when it converges to whatever your criteria is, do you stop it and then run one of these?
Yes. Yeah, those are called hybrid methods. That's very common to use them. you just you run a global optimizer for a while, and then the final answer you use that as a seed point for your local optimizer. And it's also it improves the efficiency a lot. I mean, you don't waste nearly the same amount of fitness evaluations that you would using only a global optimizer. The PSO, I told you in the PSO lecture that it's got strong global search ability but weak refined local ability. So as soon as you know that you're going to spend a lot of time just improving the answer that you currently have, you stop it. The reading material for next lecture is the paper posted on Vista and the copyrighted material, and that's just a paper by Dr. Haftka. It's fairly big. He had problems when he scanned it in. It's about a 2 meg or a 3 megabyte download each section, so if that gives anybody any problems, just send me a mail. Okay, are there any other questions? Mm.
I thought that either you can do the bonus assignment or vote, right? If you do the bonus assignment, you're voting for yourself.
Yes.
The thing is, what worries me is, see, Ben did a problem,
Yeah.
and I just saw the thing on the net, and I also did it, and I said, Oscar, why don't you vote for me? And I get more votes even though Ben did the homework before me.
Mm-hmm.
See, and I get all the points, and he gets none. So
Yeah.
So the thing is, what I thought is, if everyone does a bonus problem, and you grade, if you do the bonus problem, you don't get a chance to vote. And you say, okay, and you grade the thing based on whether you did the bonus problem right or wrong.
Yeah.
And then if some people have voted for something, somebody did a problem much better than others,
Yeah.
you can give a 20% bonus or whatever. That's what.
Yeah. Well, Dr. Hafka's whole idea behind the voting was trying to minimize the work that we have to do. I mean, if you do the assignments, the deadline is finished, and then everybody starts voting, you just pick the ones that have the most votes, and you just have to grade those two. That's the idea. Instead of grading however many problems, 3 per student, which is a lot of work, we only grade 2 or 3.
The only problem is that, and I understand that's,
Mm-hmm.
and I, as someone who's TA, I totally understand what you're trying to do. But if somebody, like if someone posts an answer, people have posted 3 answers to a question I was about to post, so I went through and read all 3 of those and made sure my answer had more detail than all 3 of those answers.
Yeah.
And just because I posted.
Yeah, you get an advantage by posting later.
Right.
Yeah, we might have to change that.
But
So why don't
eventually,
I think we can come around that by saying, don't post it before, right?
Yes.
Post it on the day of when it is due, then we can.
Or send it to me and I'll post it all simultaneously.
right.
I think that might be better. Yeah. So, yeah, and then once it's visible to everybody, everybody can start voting. I think we'll do that. I'll just discuss it with Dr. Haftka just to make sure. We'll do that. So yeah, for the off-campus students, don't send me the answers until the deadline, please, which is later for them anyway, so I don't think it'll be a problem. Okay, any other questions? Okay, thank you.